Welcome, everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to understand the various types of triangles by their angle and side measures, how to recognize congruence in geometric figures, how to use side-side-side and side-angle-side theorem to prove that two triangles are congruent, how to use ASA theorem and AAS postulate to prove that two triangles are congruent, to recognize that if two triangles are congruent, all their corresponding parts are also congruent, and to recognize congruent geometric figures as being transformations. How are we learning it? Through the Triangle Congruences notes and the Triangle Congruences assignment. When can we use this information? To recognize similarities and differences that will allow you to distinguish between solutions in your life and to group items together based on limited but similar information. How do you know you learned it? By getting a score of 4 on the Triangle Congruences assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. After that, I'll give you time to complete the Triangle Congruences assignment on Desmos. At the end of class, we'll go back over our learning goals and success criteria while you fill out your Before You Go. Your only homework for tonight is to continue working on the Triangle Congruences study guide and any incomplete assignments that you may have. Let's take a look now at the Triangle Congruences notes. The notes begin with the learning goals and success criteria. Now, what is congruence? Congruent means that two geometric figures are exactly the same, meaning that the lengths and the angles are the same. The symbol for congruent is this equal sign with the squiggly on it. So we can see that we have three triangles here, and they're all exactly the same. Now they're rotated a little bit, they're flipped around, they might look a little different, but the sizes are all the same. So they all have the same lengths. So this side and this side are the same, and this side. This side down here and this side are all the same. And all the angle measures are the same. This angle and this angle and this angle are all the same. This angle, and this angle are all the same, and so on. So triangles can be congruent even if they are not facing the same direction. So for instance, we have three triangles here, and we're given the sides and angle measures. And if they're all congruent, then we need to make sure that their corresponding sides and angles are congruent. So if this side is 1, that means this side here would also be 1 because that's the corresponding side. And then this bottom side here is 2. And the bottom now is this part here, so this side length is 2. And then the longest side, the hypotenuse here, is 3, which is this side here, so that side's 3. And then we look at the next one. So again, this side is 1, and that corresponding side in this triangle is this side here, so that side's 1. And then this bottom part here is now the top over here, so this is 2. And then this long side is 3, which is this side here, so that's 3. So notice that even when we move the triangles around, the side lengths don't change. Now, angles, we can do the same thing. So this angle here is 90 degrees. Well, the corresponding angle is this one here. This one is also 90 degrees. Then this one is 60 degrees, and its corresponding part is right here, so this is 60 degrees. And then this one is 30, and that's corresponding one is here. Then we can do it again. We have our 90-degree angle. Well, now that angle is up here, so this is my 90. Then I have my 60-degree angle, which is right here. Then my 30, which is now right here. So again, all the measures of the angles are the same as well. Now, understanding the markings. So we can use dashed lines and angle arcs to indicate the lengths and angles that are congruent. So for instance, we have this side here with a single dash. Well, we find its corresponding part and we put a single dash there. That means that this side and this side are congruent. Then we could do this one here with the double dash. And we find its corresponding side, right, which is here, and we do a double dash there. That means that those two sides are congruent. Then we do triple dash and show that those are congruent. And we can continue that on with this triangle as well. So we have single here, double here, and triple here. So that indicates that all the 3 dashes are all congruent, all the 2 dashes are congruent, and all the single dashes are congruent. Now, same thing with the angles now. Now, notice we have arcs here. If it's a 90-degree angle, then we put a box, but otherwise it would be an arc, and we could have a single, double, and we could have a triple arc as well to represent those angles. So we have our 90-degree angle here, which matches up with this one here. Then we have our single arc, which goes here, and our double arc, which goes here. That indicates that this one and this one are congruent. This angle and this angle are congruent, and this angle and this angle are congruent. And we can do it over here as well. Here's our 90. Our single arc would be here, and our double arc would be there. And again, the arcs match up the congruent angles. So we need to be able to discuss how to label each of these parts of the triangle. So the first way is the line segments are written by their two endpoints. For instance, this is AB. And then we'd have BC. So that goes from here to here. And then we have AC or CA. Either way works, and you could do it in any order. This could be BA or CB. It doesn't really matter. But we need to indicate it by the two endpoints. Now, angles are given by the two endpoints with the vertex in the middle. So, for instance, if I want this angle right here, that is ABC or CBA. Either way. But I have B in the middle. Then if I want to do the next one, I could have ACB. That represents this angle here. And then BAC represents this angle right here. So these are ways we can label the parts of a triangle. Now, understanding congruence. In order to show that two triangles are congruent, we must show that all the sides and all the angles are congruent. So first we need to state the parts that are congruent. Well, we have AB here with a single dash, and we have DE here with a single dash, so those are congruent. Now notice, I said AB is congruent to DE. I didn't say AB is congruent to ED, because that is not a true statement. In order to make a true statement, I need to follow along with the corresponding parts. So I went from the endpoint with the double arc to the endpoint with the 90-degree angle. So I need to do the same thing here. Endpoint with the double arc to the endpoint with the 90-degree angle. So it's AB is congruent to DE. Then we have BC here is congruent to EF, and AC is congruent to DF. So those show that all the parts are congruent. Then I have my angles. Angle ABC is congruent to angle DEF because they're both 90 degrees. They both have the box. Then I have angle ACB, so the single arc, is congruent to DFE, single arc as well. And then I'll do my double arc. So BAC is congruent to EDF, and those are congruent. So now we've shown that all the sides and all the angles are congruent, so therefore the triangles are congruent. So we can now say that triangle ABC is congruent to triangle DEF. Now, one of the properties of triangles says that the total amount of all the angles should end up being 180 degrees. So for instance, we have a triangle here. This one's 90, 60, and 30. If we add all those together, we get 180 degrees. Now, the different types of triangles. So the first kind is an equilateral triangle. An equilateral triangle has all three sides congruent, and all three angles are congruent. Isosceles triangles have two sides congruent and two angles that are opposite of those sides congruent. And then lastly, we have a scalene triangle where no sides are congruent and no angles are congruent. So what do these look like? Equilateral, remember, is all sides congruent, all angles congruent. So it looks like this. So all the sides are the same and all the angles are the same. Isosceles triangle has two sides, this side and this side the same, and the opposite angles the same. Scalene is just kind of random. All the sides, all the angles are different. Other types of triangles, we have right triangles, where one of the angles is a right angle or a 90-degree angle. Acute triangles have all angles smaller than 90 degrees. And an obtuse triangle has one of the angles bigger than 90. So what does this look like? Right triangle has a 90-degree angle right here. Acute triangle, all the angles are smaller than 90. So in this case, they're all 60, but they don't have to all be the same. They just need to all be smaller than 90. And then obtuse has this big angle here that's bigger than 90, right? Because if I were to draw a right angle, it would go up like this, and it's definitely bigger than that. So that's an obtuse triangle. Now the question is, what if we don't have all that information? What if we don't know all the sides and all the angles? Can we still prove that two triangles are congruent? So in this case, we have no angles and all the sides. So we have three sides we know are congruent, but does that mean necessarily that the angles are congruent? So we know that AB is congruent to DE. We know that BC here is congruent to EF. And we know that AC is congruent to DF. And that's based on the markings here. So can we say that the triangles are congruent then? Well, in fact, we can. And it's by using this concept of SSS congruence, or side-side-side congruence. And what side-side-side congruence says is that if we know that all the sides are congruent, then the triangles must also be congruent. So again, we can say that AB is congruent to DE. We could say that BC is congruent to EF, and AC is congruent to DF. Therefore, we know that the triangles must be congruent because all of the sides are congruent. So because of side, 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 we know that triangle ABC is congruent to triangle DEF. So what if we know that two sides are congruent and one angle is congruent? Well, in this case, we can see that we have AB is congruent to DE. We can see that BC is congruent to EF. And then we have this angle here, so we have angle ABC is congruent to angle DEF. Does that mean that the triangles are congruent? Well, in fact, it does. And it's by using this idea of side angle side, or SAS congruence. So side angle side congruence says that if we know that two sides and the angle between them are congruent, then the triangles are congruent. Now notice here, I have a side, an angle, and a side. The order matters. If I had a side, this side, and I knew this angle, then this theorem would not work. The only way it works is if we have the two sides and the angle that goes between them. So here we know that AB is congruent to DE, and between them we know that there's an angle here, angle ABC, that's congruent to angle DEF, and then we know that side BC is congruent to side EF. Therefore, we have two sides and an angle between them that are congruent, so therefore we can say that triangle ABC is congruent to triangle DEF. Now, once again, what if we don't have all the information? What if we know that two angles are congruent and a side is congruent, but we don't know anything else? Can we still prove that the triangles are congruent? So, in this case, we could see that side AB is congruent to side DE. And then we can see that angle ABC is congruent to angle DEF. And then we have angle BAC is congruent to angle EDF. Now, does that mean that the triangles are congruent? In fact, it does. And it's because we use this theorem called the angle side angle theorem, or ASA congruence theorem. And the angle side angle congruence says that if we know two angles and the side between the two angles are congruent, then the triangles are congruent. So if you notice, we have an angle, a side, and an angle. Again, order matters. So we have the side that we know comes between the two angles that we know. So then let's restate what we know. Well, we know side AB is congruent to side DE. We know angle ABC is congruent to angle DEF. And we know angle BAC is congruent to angle EDF. So therefore, we have two angles and a side between them that are congruent, so we can use the ASA theorem to state that the triangles are congruent. So we can say triangle ABC is congruent to triangle DEF. Now, what if we know two angles and a side, but the side is not between them? Can we still prove that those are congruent then? So here we have angle, angle, and a side, or a side, angle, angle, however you want to look at it. So can we prove that those triangles are congruent? Well, first, let's state what we know. We know that angle ABC is congruent to angle DEF. We know that angle BAC is congruent to angle EDF. And we know that AC is congruent to DF. So does that mean that the triangles are congruent? Well, once again, in fact, it does. And it's by using this idea of angle side congruence. So this says that if we know two angles and then the side after those two angles, then we know that the triangles are congruent. So here we have angle ABC is congruent to angle DEF. We have angle BAC is congruent to angle EDF. And we have side AC is congruent to side DF. So we have two angles and the side that comes after them are all congruent. So therefore, we would say the triangles are congruent. Triangle ABC is congruent to triangle DEF using angle side. Now, what does CPCTC mean? Well, CPCTC means that congruent parts of congruent triangles are congruent. So that's kind of a mouthful. What this basically means is that if we know that two triangles are congruent, then their parts must also be congruent. So as long as I've stated, okay, triangle ABC is congruent to triangle DEF, then we could say that side AB is congruent to side DE, because if the triangles are congruent, then that means their parts also have to be congruent. So for instance, if I told you that these two triangles are congruent, then we could say that this side and this side are also congruent. If I said that the triangles were congruent, then we could say that this side here and this side here are congruent, and this side here and this side here are congruent. We can also say that the angles are congruent. So we could say that this angle and this angle are congruent, and this angle and this angle are congruent, and this angle here and this angle here are congruent. So because we know that the triangles are congruent, then we can find their corresponding parts and say that they're congruent as well. And the reasoning for that is CPCTC. Congruence and transformations. If we know that two triangles are congruent and their parts are congruent, we can look at those congruent triangles as transformations. So if a triangle is translated, reflected, or rotated, it will be perfectly matched up with its congruent triangle. So whatever transformation occurred, if we undid it, it should end up back on top of itself and look exactly the same. Now here's a little video. We have translation. Notice every person in here is the same. They don't change shape or size, but they are sliding around. They're sliding side to side. They're moving front to back. Those are translations. So it is a slide of a figure or a point. So for instance, we have a triangle here. And if we slid it to the right and up, it would end up being this triangle here. So it's just a slide movement. So introduction to translations, here's our triangle. If we were to slide it, it could move and look like that. Or we could slide it down. Or we could slide it to the left. So all of these are translation movements. Translations are slide movements, and it does not change size, shape, or position. Notice it doesn't change direction. It doesn't flip and turn. It doesn't flip over. It doesn't rotate at all. It's exactly the same. It stays, the top stays the top, the bottom stays the bottom, the left side stays the left side, and the right side stays the right side. It just slides around. Now here's a little video of Simbo looking at his reflection in the water. So that's what a reflection is. Reflections occur when we flip a figure over a point or a line. So for instance, we have a triangle here. If we flip it over this line, it's going to flip downward and look like this. So that's a reflection. So introductions to reflections. Reflections over a line, we start with, for instance, a triangle here. If we flip it over, it becomes like this. So if we flip it over that line, it becomes this way. So it can be up and down, or it could be side to side. So it could flip and go over here as well. Notice they do not change size or shape. They do change direction though. So it will flip over and it will look inverted, but the size of the triangle in this case does not change. Now what is a rotation? A rotation looks like this. So we have Woody's head here and it spins around. So rotations are spin movements. So it's a spin of a figure around a point. So we have a triangle here. If we were to spin it, it ends up being this triangle here. Now, introduction to rotations. We have our triangle here. If we were to spin it to the right, it would look like that. If we were to spin it again, it looks like that, and again, right there. So we're just rotating and spinning that triangle. So rotations are spin movements about a point in which the object moves and it doesn't change size or shape. So notice the triangle is exactly the same size, but it does change direction. Now, what is a geometric proof? A geometric proof is a step-by-step explanation that uses definitions, properties, postulates, and previously learned theorems to draw a conclusion about a geometric statement. A geometric proof is typically done in a two-column proof with one column being the statements and the other being the reasons. So what do geometric proofs look like? They look like this. So we have a column here that represents our statements. This is what do we know? So these are the statements of we know this, we know that, and so on. Now the right side is the reasons, and that is the arguments for how we know that to be true. This is an example of a geometric proof. So it says AB is congruent to DE, and we have our reason as given. Given information is the information that they told us. So whether it's a marking or they state it in words, whatever it is, the given information is stuff that we didn't have to figure out on our own. It was told to us. Then we have AC is congruent to DE, given. Angle BAC is congruent to angle EDF, given. And then the triangles are congruent. Notice all of this was given information, but this part we had to come up with on our own, the SAS theorem, to prove that those triangles are congruent. So we use the theorems and postulates to fill in the rest of it. Let's take a look now at the Triangle Congruences assignment. The assignment begins with the learning goals and success criteria. If we scroll down, there's a link here to take us to the Desmos activity. Go ahead and click on that link, and it should take you to a page that looks like this. We'll go ahead and click Start the Activity. The activity begins with the learning goals and success criteria. We'll go ahead and click Next. Now, for each of these, we're going to decide which theorem we would use to prove that the triangles are congruent. And for some of them, there may be multiple correct answers. So let's say for this one, we said it's SSS theorem. We hit check it. It tells us to try again. We say that one and ASA, still incorrect. Now, we can use all of them for this one, so it tells us good job. So we answer that for each of these. We'll do it for this slide as well, and this one. Now for this one, we're given two triangles, and we need to prove that they are congruent. So we're given a partial proof here, and it says AB is congruent to what? Well, we can see that AB here is congruent to DE, so I'm going to go here and type in DE. And then we give the reason. How do we know that? Well, they have the symbols here. We didn't have to think about it, so that is what we consider given information. Then BC is congruent to, so BC is congruent to EF because they both have the double bars. So we'll go ahead and put that in, and that's given. And then here, AC is congruent to DEF. And how do we know that? Well, they gave us the symbols again, so that's given information as well. So there's my given information. And now I can say triangle ABC is congruent to triangle DEF. And how do we know that? Well, we know that all three sides are congruent, so we would say that is the SSS theorem. We can hit check it. It shows us what it should look like. And then we'll do the same thing for this one. So we're given two triangles, and we need to fill in the proof. So we're given some information here, and we need to fill in the rest of the statement. So it says angle CAB is congruent to what? So we have angle CAB is congruent to angle FDE. So we're going to put in angle. I'm going to copy this. Copy. So angle FDE. And how do we know that? Well, because of the little arcs in the corner. So that's given information. Then we have AB is congruent to DE. So we'll type in DE. And that is also given information because of the little dashes here. Then we have angle ABC. So ABC is congruent to angle DEF because of the double arcs. So we'll copy the angle symbol. And we'll put in DEF. and that's given information as well because of the double arcs in the corner. Then we can say that triangle BAC is congruent to triangle EDF. So we'll go ahead and put that as our answer, EDF. And how do we know that? Well, it's angle, side, angle. So we put angle, side, angle theorem. We hit check it, and we can see that all of our stuff matches up, so we did it correctly. And then when you're done with that activity, you'll go ahead and go back to your Google form and click next. This will take you to your before you go. Go ahead and fill out your before you go, and then submit your work on Google Classroom.